Welcome back to the Explainer. Let's just jump right in today. If you've ever looked at a complex DC circuit diagram and immediately felt kind of overwhelmed by the sheer maze of wires, batteries, and resistors, yeah, you're definitely not alone. It looks like a lot. But today, we're literally going to change how you see those diagrams. We're building what I like to call the Circuit Detective's Toolkit. We're taking the core principles of DC circuits and Kirchhoff's laws and breaking them down into a highly manageable, super logical set of tools.
Okay, so the big question before we dive in, how do we actually make sense of a complex electrical circuit without losing our minds? When you're staring at all those intersecting lines and voltage readings, it just looks like pure chaos. But here's what I want you to do. Reframe it right now. Think of circuit analysis not as some confusing web, but as a puzzle. And the absolute best part about this specific puzzle? There are no hidden tricks, no magic happening behind the scenes, just fundamental, unbreakable physical patterns that are quite literally waiting to be decoded. Once you know the rules, the circuit has no choice but to reveal its secrets to you. All right, here is our agenda for today. We've got 4 main concepts to cover. 1. Power and internal resistance. 2. Conservation of charge. 3. Conservation of energy. And 4, calculating combined resistance. Let's get to it. Section 1, power and internal resistance. So let's start right at the source, the battery. You know, most of us just kind of assume a battery is this perfect, infinite fountain of energy. But the reality? Batteries have what we call internal resistance, represented by a lowercase r. See, they're made of physical stuff, chemicals, metals, electrolytes, and these materials naturally resist the flow of electricity, exactly like a standard resistor in your circuit does. So it's not a perfect fountain. It's actually got its own internal friction. And this is absolutely crucial to understand because it causes a drop in voltage the second current actually starts flowing. It essentially dictates the absolute maximum power your battery can deliver to the external circuit, which we call the load. Now, what's really fascinating here is the core principle of power delivery. Our source material highlights this really interesting graph showing power delivered to a load against the resistance of that load. And it's not a straight line. It's a curve with a very distinct peak. What does that mean for us? It tells us that a battery hits maximum power delivery under one very specific, honestly, mathematically beautiful condition. It happens exactly when the external load resistance, that's capital R, perfectly equals the battery's internal resistance, lowercase r. Think about it. If your external resistance is too low, you're wasting most of your power just fighting the internal friction of the battery itself. Too high, the current drops so low that, again, barely any power is delivered. That sweet spot, the absolute peak, is right when capital R equals lowercase r. Let's look at how this plays out in a real scenario with worked example 10b. Imagine you hook up a voltmeter to a lonely battery, and it reads 13.0 volts. Okay, that's our pure EMF. Now you connect a lamp that draws 3.0 amps, and suddenly the voltage drops to 12.0. Wait, where did that missing volt go? Well, it was quote-unquote lost, overcoming the battery's own internal resistance. So using the formula V equals I times R, we just take that 1.0 lost volt, divided by our 3.0 amps, and boom, we get an internal resistance of 0.33 ohms. Mystery solved. Moving on to Section 2, Conservation of Charge. This brings us to Kirchhoff's first law. The formal definition goes like this. The sum of the currents entering a junction in a circuit is always equal to the sum of the currents leaving the junction. Sounds simple enough, right? But the implications are huge. Why does this happen? Well, remember, current is just the rate of flow of electric charge. We're talking about physical electrons moving through a wire. They can't just vanish into thin air, and they definitely can't pile up in an intersection like cars in a traffic jam. Whatever flows in absolutely must flow out. It's the law. Charge is perfectly conserved. So when we look at a parallel circuit where a wire splits off into different paths, we get this wonderfully straightforward equation. Total current I equals I1 plus I2 plus I3, and so on. In parallel, the current just divides up to take those alternative routes. But, and here's the kicker, no matter how many branches you have, if you measure the current in every single one of those little branches and add them all together, they will perfectly match the total current that entered the junction to begin with. The flow splits, sure, but the total amount of charge moving through the system, totally constant. Let's track this current like water flowing through diverging pipes to see how we can decode a diagram. Let's say we start with 175 milliamps entering from the power supply. That means exactly 175 must be flowing out. Okay, at the first junction, one branch pulls off 75 milliamps. Basic subtraction tells us the main branch has to keep the remaining 100, right? Now, follow that 75 milliamp branch to the next junction.
25 milliamps go one way, which means, you guessed it, the final unknown path has to take the remaining 50. By literally just tracking what goes in and what comes out, we decode the entire network. Easy.
All right, Section 3, Conservation of Energy. Now we step up to Kirchhoff's second law, which is basically the conservation of energy, just applied to an electrical loop. The formal definition is the sum of the electromotive forces in a closed circuit is equal to the sum of the potential differences. Think about the actual journey of a charge. When it flows through a battery, it gains electrical energy. That's your electromotive force, or EMF. But as it travels through the rest of the circuit, through the wires, the lamps, the resistors, it naturally loses that energy, giving it off as heat or light. That loss is our potential difference, or PD. Kirchhoff's second law is just saying that the energy gains from the power source has to perfectly, 100% balance out the energy lost across the components in any closed loop. So how do we actually use this? Think of it like supply and demand. The total energy supply, our EMF, capital E, has to equal the total energy demand. That's the potential difference across component 1, V1, plus the potential difference across component 2, V2. And since we know that V equals I times R, we can expand it. Supply, E, equals current times R1 plus current times R2. This is huge because it turns an abstract energy concept into something we can actually calculate. If you know the EMF and your resistance values, you can find the current. It literally ties the whole closed loop together. But what if you have two batteries in the loop and they're fighting each other? Well, direction matters. You just subtract their opposing EMF values to find the real driving force. So a 3.0 volt cell minus a 1.5 volt cell gives us a net push of 1.5 volts. We set that 1.5 equal to our energy losses, which is our current I times the total resistance of 6.0 ohms. 1.5 divided by 6.0 gives us a current of 0.25 amps. And here is a super cool side note from the source material. Because that weaker 1.5 volt cell is actually having current forced backward through it by the big 3.0 volt cell, it's not supplying energy at all. It's actually being recharged. How cool is that? Finally, Section 4, Calculating Combined Resistance. Before we crunch any numbers here, we have to spot the structural differences. In a series circuit, it's just one continuous, unbroken loop. The current is exactly the same everywhere. But in a parallel circuit, the current has options. It splits into alternative routes. However, and this is key, because components in parallel are connected across the exact same two main junction points, the potential difference, the voltage, across those parallel branches is identical. So how does this translate into our math shortcuts? Well, for series circuits, since the voltage just adds up along the path, the total resistance is simply R1 plus R2 plus R3. You just add them right up. Super simple. Parallel circuits are the inverse. Because voltage is constant across all those branches, we divide it out, which leaves us with this formula. 1 over total R equals 1 over R1 plus 1 over R2 plus 1 over R3. Those two little formulas, they are absolutely your master keys for unlocking and simplifying even the messiest circuit diagrams. Let's take a quick step back and look at the full circuit toolkit we've built today. Number 1, we unlocked the battery. Maximum power transfer happens only when the load resistance equals the internal resistance. Number 2, Kirchhoff's first law. Whatever current enters the junction has to leave it. Charge is conserved. Number 3, Kirchhoff's second law. In any closed loop, the energy gained from the EMF perfectly equals the energy lost across the components. And number 4, we know exactly how to combine resistors in series and parallel. Together, these tools take a chaotic, scary-looking wiring diagram and turn it into a totally predictable, logical, and highly solvable system. By systematically applying these 4 tools, you are no longer just guessing at numbers. You are literally reading the physical laws of the universe written right there into the wires. Armed with these foundational rules, what hidden codes are you going to be able to decode in your next circuit diagram? Seriously, I challenge you to take this exact toolkit approach into your own studies. Look for the junctions, trace those closed loops, spot the series and parallel clusters, and just watch the puzzle piece itself together. It's incredibly satisfying once it clicks. Thanks so much for hanging out with me today to explore this. Keep learning, keep analyzing those patterns, and I'll catch you on the next explainer.